A Venn diagram is a visual representation of sets. The concept of Venn diagrams was introduced by an English mathematician, John Venn. Venn diagrams are represented with the help of closed figures such as circles, ellipses, and rectangles. Let's draw a Venn diagram for the sets shown. We represent each set within a circle. The circle representing A consists of the elements 2, 5, 6, and 7. Each number is represented with a dot, with the respective number written next to it. The circle representing set B consists of the elements 3, 8, 9, and 10. One of the universal sets of these two sets is the set of natural numbers. So we include these two circles in a rectangle that represents the universal set, that is, the set of natural numbers n. Now, the Venn diagram is complete. Sometimes, we may need to represent two or more sets having common elements using Venn diagrams. For example, A is the set of prime numbers less than 10, and B is the set of prime divisors of 26. The collection of elements of sets A and B are as shown. These sets are represented in circles A and B as shown. If we observe, the element common to both the sets is 2. So we overlap the circles on each other as shown. The common region of the two circles will have the element 2, which is common to both the circles. In this module, you will learn about the different operations that can be performed on sets. While we come across many sets in mathematics, it is evident that many sets share the same elements. We can perform various operations on sets. Examples of operations are union of sets, intersection of two or more sets, difference of two sets, and complement of a set. Let us learn these operations in more detail. Let P and Q be two sets. The union of sets P and Q is a set that consists of the elements from both the sets. Let's perform the union operation over sets P and Q. The elements of sets P and Q are listed out one by one. The repeated elements are written only once. Here, 5 in both the sets is written only once. Hence, set P union Q consists of all the elements of sets P and Q. The definition of union can be as follows. The union of two sets A and B is set C, which consists of all those elements that are either in A or in B. Symbolically, the union of sets A and B is represented as shown. The Venn diagram representation of two sets A and B is as shown. The shaded region represents the union of the sets A and B. Observe that both the circles are shaded since set A union B consists of all the elements of sets A and B. Some of the properties exhibited by the union of two sets are as listed. The union of two sets follow the commutative law. The union of three sets follow the associative law. The result of the union of a set with a null set is the set itself. The union of a set with the same set follows the idempotent law. The union of a set with the universal set results in the universal set itself. Let's discuss the intersection of sets. Let's consider the same sets P and Q, which we saw before. If we consider the set of common elements of sets P and Q, then we can say that the set is formed by P intersection Q. In sets P and Q, the common element is 5. Therefore, the intersection of sets P and Q is 5. The definition of intersection is as follows. The intersection of two sets, A and B, is the set of all those elements that belong to both A and B. Symbolically, the intersection of sets A and B is represented as shown. The Venn diagram representation of intersection of two sets A and B is as shown. The shaded region represents the common elements belonging to the two sets. Here is an interesting property of the intersection of sets. Let's consider two sets C and D. We can observe that there is no common element among the sets C and D. Therefore, C intersection D is a null set. We can say sets C and D are disjoint sets. The Venn diagram representation of sets C and D is as shown. Some properties of the intersection of two sets are as follows. The intersection of two sets follow the commutative law. The intersection of three sets follows the associative law. The intersection of a set with a null set results in the null set. The intersection of a set with the universal set results in the set itself. The intersection of a set with itself follows the idempotent law. Intersection is distributive over union. This property can be verified with the help of Venn diagrams. Taking the left-hand side, for B union C, we have this Venn diagram. A intersection B union C is as shown. On the right-hand side, the Venn diagram for A intersection B is as shown. The diagram for A intersection C is as shown. For A intersection B union A intersection C, the Venn diagram is as shown. Next, we will discuss about the difference of two sets. Consider two sets X and Y as shown. The difference of sets X and Y taken in the same order is denoted as shown. The difference of sets Y and X taken in the same order is denoted as shown. First, we will find the difference of sets X and Y taken in the same order. This means we have to find the elements that are present in X but not in Y. The elements that are in set X but not in set Y are 2, 3, and 4. Therefore, set X minus Y has the elements 2, 3, and 4. Next, we find the difference of the sets Y and X taken in the same order. This is found by taking the elements that are present in Y but not in X. These elements are 7 and 8. We can observe that X minus Y is not equal to Y minus X. Set X minus Y is represented through a Venn diagram as shown. Observe the shaded portion. Only the region of set X, which is not shared by set Y, is shaded. Similarly, the Venn diagram for Y minus X is shown here. Only the region of set Y, which is not shared by set X, is shaded. The difference of any two sets, A and B, taken in order, is represented symbolically as shown. Similarly, B minus A is written symbolically as shown. The concept of the difference of two sets can be extended by replacing one of the sets with the universal set. Let's see an example to understand this. Let us consider the set of natural numbers. We can consider the set of whole numbers a universal set for the natural numbers. The difference of sets W and N is the complement of set N. The complement is denoted as shown. Therefore, the complement of set N with the universal set being the set of whole numbers is a singleton set with 0 as the element. Let U be the universal set and A be a subset of U. Then, the complement of A is the set of all elements of U that are not the elements of A. The complement of a set A is symbolically represented as shown. The Venn diagram representation of the complement of a set is as shown. The shaded region represents the complement of set A. It should be noted that the complement of a set depends on the universal set. For example, let's find the complement of the set of natural numbers with the universal set being the set of integers. The complement of set N is shown here. A few observations on complements of sets. If A is a subset of the universal set U, then its complement, A dash, is also a subset of U. The complement of the union of two sets is the intersection of their complements, and the complement of the intersection of two sets is the union of their complements. These are called De Morgan's laws. The complement laws are as follows. The law of double complementation says that the complement of any set is the set itself. The laws of empty set and universal set are as shown. In this module, you will see how the knowledge of sets can be applied to solve practical problems. We have already seen the operations performed on sets, such as intersection, union, and difference of two sets. Let us verify some results based on these relations. To begin with, we will verify the relation N of A union B is equal to N of A plus N of B, provided A and B are disjoint sets. Let's verify the relation using an example. Let's consider two sets A and B. These sets are disjoint sets since there are no elements in common. The number of elements in set A is 4. The number of elements in set B is 5. The union of the sets consists of the elements as shown. The number of elements in the set A union B is 9. Now, we can see that the number of elements in set A union B is equal to the sum of the number of elements in sets A and B. Therefore, the relation is verified. Next, we will verify another relation shown here. The relation holds provided sets A and B are finite sets. Let's verify the relation with the help of a Venn diagram. From the figure, we can observe that the sets A minus B, A intersection B, and B minus A are disjoint sets. Also, the union of these three sets results in the set A union B. We will use this fact to obtain our original relation. It follows that the number of elements of set A union B is equal to the sum of the number of elements of each set taken independently. We will add and subtract n of A intersection B as shown. From the figure, we can observe that the sum of elements in the sets A minus B and A intersection B is equal to the number of elements in set A. Similarly, the sum of elements of the sets B minus A and A intersection B is equal to the number of elements in set B. Therefore, we get the following equation. Hence, the relation is verified. We will now verify this relation. Momentarily, let's denote B union C with the letter D. This can be written as shown. Now, we will replace the letter D with B union C. The third term can be written in the form shown using distributive law. Therefore, we can write the expression as shown. Now, we expand the second term on the right-hand side. The third term can be expanded as shown. Hence, the relation is verified. We will see some practical situations where we can use these relations. In a village, 150 people subscribe to 150 people subscribe to Indian language dailies, 75 to English dailies, and 45 to language as well as English dailies. Find the number of people who subscribe English or language dailies. In the set theory, the word "and" suggests an intersection, and the word "or" suggests a union of sets. Let V be the set of people who subscribe to language dailies, and E be the set of people who subscribe to English dailies. Let V intersection E be the set of people who subscribe to English and language dailies. We have to find the number of people who subscribe to either English or language dailies. The number of elements in each set is as shown. We will use this relation to find the number of people who subscribe either to English or language dailies. Substituting the values, we get the number of people who subscribe either to English or language dailies as 180. Let's see another problem. On a particular day, 300 students visit cafeteria. 110 students go there for lunch. 225 students have snacks, and 50 students have both lunch and snacks. Find out the number of students who had lunch but not snacks, snacks but not lunch, either lunch or snacks. Let U be the universal set of all the students who attended the cafeteria. The number of students in this set is 300. Let A be the set of students who attended the cafeteria for lunch. The number of students of this set is 110. Let B be the set of students who attended the cafeteria for snacks. The number of students of set B is 225. The number of students who had lunch and snacks is given by A intersection B. The number of students who belong to this set is 50. Now, we will find the number of students who had lunch but not snacks. From the Venn diagram, this is given by the set A minus B. The number of elements of this set is given by the number of elements of set A minus the number of elements of set A intersection B. Using the values, we get the number of students who visited the cafeteria only for lunch as 60. Next, we will find the number of students who had snacks but not lunch. This is shown by the shaded region in the Venn diagram. The number of elements of this set is given by the relation shown. Using the values, we find that 175 students had snacks but not lunch in the cafeteria. Now, we will find the number of students who had either lunch or snacks. This is given by set A union B. This is given by the relation shown. Using the values, we get the number of students who had either lunch or snacks as 285.